final question on the study guide, number 21, we're given the graph of f prime at the top, and we can see from the description that we have a line, then a quarter circle, and then two more line segments after that. Part A actually has a typo. It says find the average rate of change of f. There really should be a mark there. It's f prime. Find the average rate of change of f prime from x equals -5 to x equals 5. Okay, so let's go ahead and do that. So we're looking for the average rate of change of f prime. So that means we want f prime of the larger value, f prime of 5, minus f prime of -5 over 5 minus -5. Now, f prime of 5, so 1, 2, 3, 4, 5, that's this point right here, which we see is 1, 2, 3, 4 units up. So that means that we have 4 minus, and now we want f prime of -5, so 1, 2, 3, 4, 5 units back, 1, 2, 3, 4 units down, so that's -4. So we have 4 minus -4 over 5 minus -5, so that's 8 over 10. We don't need to simplify any further because we don't need to simplify our answers on this section. Okay, so does the mean value theorem guarantee some number c between -5 and 5 such that the second derivative is equal to 8/10? All right, why or why not? Okay, well, let's go look at our graph. Here's the graph of f prime. The mean value theorem guarantees that we're going to have a tangent line to this curve which is equal to 8/10 as long as the function is continuous over the entire interval, including the endpoints, and differentiable in the interior of the interval. Well, f prime is definitely continuous, as we can draw the entire graph without taking the pen off the paper. However, we have not one, not two, but 3 points along f prime where f prime is not differentiable because of either the cusps or the corner. All right, so that is a huge issue here. So we're going to say no, and it says why or why not. Okay, because f prime is not differentiable, right, and let's go back and check out those values. So we have this value right here when x is equal to -2, this value right here when x is equal to 0, and then this value right here where x is equal to 3. So because f prime is not differentiable at x equals -2, 0, or 3. Part B, on what open intervals, if any, is the graph of f concave up? Justify your answer. So f is concave up when f prime is increasing. Right, so we need to determine when, if at all, f prime is increasing. Go back to our graph. We see that f prime is increasing at the start of the domain, then it decreases, then f prime increases again, and then it remains constant. So the first derivative is increasing from -5 up to -2, and also from 0 up to 3. And notice how they remind us that we want open intervals here. So f is concave up on -5 to -2 and 0 to 3 because f prime is increasing. And finally, part C, find all values on the interval from open interval from -5 to 5 at which f has a critical point. Okay? Critical points occur when the first derivative is equal to 0 or does not exist. Well, this first derivative always exists. We already talked about that. It always exists between -5 and 5. When does the first derivative equal 0? Here and here. So at x equals -2 and x equals 1. All right, so find all the values in which f has a critical point. F has a critical point at x equals -2 and x equals 1. Okay. It doesn't say that we have to say why, we just have to identify them. Now, classify each critical point as a location of a relative max, relative min, or neither. Okay, so at x equals -2, let's go back. When x is equal to -2, our derivative is negative before and after. Our derivative does not change sign. Since the derivative does not change sign, that means the critical point is neither a local max nor a local min. Okay, so we have to state that it's neither. All right, the critical point is neither. All right, and then we have to justify the answer. Why? Because f prime does not change sign. All right, how about at x equals 1? All right. Well, at x equals 1, the derivative was negative beforehand and positive afterwards. We know that when the derivative changes from negative to positive, that results in the original function having a relative min. So at x equals 1, f has, put a comma there, has a local minimum. Because, oops, that's therefore, because f prime changes from negative to positive.